Hi, my name is Suzanne Aldrich. I'm a solutions engineer at Cloudflare, which is a company that provides DNS and CDN services for websites around the world. Today's discussion is an anatomy of a DDoS. I want to talk about DDoS attacks because they make headlines every day, but many people don't know how they work and how you can defend against them. DDoS attacks can be high-volume UDP traffic floods, Syn floods, NTP amplification, or Layer 7 HTTP attacks, amongst many others. Understanding how to protect yourself from DDoS is critical to doing business in the world today. This talk will cover how these attacks work, what is being targeted by the attackers, and how you can protect yourself from them. What is a DDoS attack? From a high level, a DDoS attack is like a traffic jam clogging up the highway, preventing normal traffic from arriving at its desired destination. A distributed denial of service attack is a malicious attempt to disrupt normal traffic of a targeted server, service, or network by overwhelming the target or its surrounding infrastructure with a flood of internet traffic. These attacks achieve effectiveness by using multiple compromised servers as sources of attack traffic. Exploited machines can include computers or other network devices like IoT. The motive behind these attacks are often based on political, social, or religious animus, or utilized for financial gain, such as when hackers threaten a website owner to pay a ransom with cryptocurrency, or else they'll take their website down. Cloudflare engineers have witnessed some of the largest DDoS attacks in history unfold. In the winter of 2016, we mitigated the largest Layer 3 DDoS attack to date. We were not only able to mitigate it, but actually accurately measure and analyze it. DDoS attacks take all shapes and forms. In a 400 gigabit per second amplification attack, an attacker utilized 4,500 NTP servers to amplify an attack from a small 87 megabit per second source server. Cloudflare has been fighting DDoS attacks for over 5 years. Back in 2013, the 120 gigabit per second on Spamhaus was considered a big attack, and we were able to keep the website online. DDoS attacks are evolving in size and complexity. 2016 saw 3 attacks over 1 terabit per second. One of these was launched at Cloudflare, and we successfully protected our client. 10 days later, a similarly sized attack launched through the Mirai botnet brought down a good part of the North American internet. How does a DDoS attack work? A DDoS attack requires an attacker to gain control over a network of online machines to carry out an attack. Computers and other machines, such as IoT devices, are infected with malware, turning each one into a bot or zombie. The attacker has remote control over the group of bots, which is called a botnet. Botnet means a robot network. Once a botnet has been established, the attacker is able to direct the machines by sending instructions to each bot via remote control. When the IP address of a victim is targeted by the botnet, each bot will respond by sending requests to the target, potentially causing the targeted server or network to overflow capacity. This results in a denial of service to normal traffic. Because each bot is a legitimate internet device, it can be difficult to separate attack traffic from normal traffic. What are common types of DDoS attacks? Different DDoS attack vectors target varying components of a network connection. In order to understand how different DDoS attacks work, it is necessary to know how a network connection is created. A network connection on the internet is composed of many different components or layers. Like building a house from the ground up, each step in the model has a different purpose. The OSI model, or Open Interconnection Model, is a conceptual framework used to describe network connectivity in 7 different layers. This model helps to reduce complexity when speaking about networks. Layer 1 is the physical medium for transferring data. This is the bits and the bytes that are going over electrical pulses on a wire, light transmission. This includes Cat5 cables, Wi-Fi networks. The layer 2 is where we have switching and MAC addresses. This is how we get the bits onto the network. Layer 3 is IP addressing. This includes the network interface cards, routers, and is a combination of hardware and software. The protocols involved are IPv4 and IPv6. Layer 4 is the transport layer. Well-known areas are TCP, UDP, and port numbers start becoming important. Layer 5 is the session layer, which is responsible for managing the initiation of a transfer and tearing down the network connection. Layer 6 is presentation. This is where data can be encrypted for use by the higher layer. And finally, we have layer 7 for application. This is where HTTP, SMTP, and DNS are. Attackers exploit the different layers. Layer 3, often attacks come in the form of floods, like reflection and amplification attacks. Layer 4, we see attacks like TCP Syn Flood. Layer 7, you see HTTP flood requests, attacks from tools like Slow Loris, and DNS floods. Let's talk first about application layer attacks. These are sometimes referred to as Layer 7 DDoS attacks. The goal is to exhaust the resources of the target. This is the layer where web pages are generated on the server and delivered to the client. A single HTTP request is cheap to execute on the client side. A single HTTP request is cheap to execute on the client side and can be expensive for the server to respond to, as it must load multiple files and perform a database query. Layer 7 attacks are hard to defend against, as the traffic can be difficult to flag as malicious. An HTTP flood attack is like pressing refresh in a web browser multiple times from multiple computers at once. Large numbers of HTTP requests flood the server, resulting in the denial of service. This type of attack ranges from simple to complex. Simpler implementations may access one URL with the same range of IP addresses and using the same referrers or user agents. Complex versions may use a large number of attacking IP addresses and target random URLs using random referrers and user agents. Another type of attack are protocol attacks. They are also known as state exhaustion attacks, and they cause a service disruption by consuming all the available state table capacity of web application server or intermediate resources like firewalls and load balancers. Protocol attacks utilize weaknesses that exist in Layer 3 and Layer 4 of the protocol stack to render the target inaccessible. For example, a Syn Flood attack. A Syn Flood attack is like a worker in a supply room receiving requests from the front of the store. The worker receives a request, goes and gets the package, and waits for confirmation before going back to the front of the store. The worker then gets many more package requests without a confirmation until they can't carry any more packages. They become overwhelmed and requests start going unanswered. Volumetric attacks. These are attacks that attempt to create congestion by consuming all available bandwidth between the target and the larger internet. Large amounts of data are sent to a target using a form of amplification or another means of creating massive traffic, such as requests from a botnet. One type of attack that's volumetric is a DNS Amplification Attack. A DNS Amplification Attack is like if someone were to call a restaurant and say, "I'll have one of everything. Please call me back and tell me my whole order." Where the callback phone number they give is the target's number. With very little effort, a large response is generated. By making a request to an open DNS server with a spoofed IP address, the real IP address of the target IP address then receives a response from the server. The attacker structures the request such that the DNS server responds to the target with a large amount of data. As a result, the target receives an amplification of the attacker's initial query. how are DDoS attacks mitigated? Mitigating a multi-vector DDoS attack requires a variety of strategies in order to counter different trajectories. Generally speaking, the more complex the attack, the more likely the traffic will be difficult to separate from normal traffic. The goal of the attacker is to blend in as much as possible, making mitigation as inefficient as possible. Mitigation attempts that involve dropping or limiting traffic can indiscriminately may throw good traffic out with bad. And the attack may also modify and adapt to circumvent mitigations. In order to overcome a complex attack, a layered solution will give the greatest benefit. One solution available to virtually all network admins is to create a black hole route and funnel traffic into that route. In its simplest form, when black hole filtering is implemented without specific criteria, both legitimate and attack traffic is routed to a null route or black hole. It is dropped from the network. If an internet property is experiencing a DDoS attack, the property's internet service provider may send all the website's traffic into a black hole as a defense. Rate limiting the number of requests a server will accept over a certain time period is also a way of mitigating denial of service attacks. While rate limiting is useful for slowing web scrapers and for mitigating brute force attempts at login, it alone will likely be insufficient to handle a complex DDoS attack effectively. But rate limiting is a useful component in an effective DDoS mitigation strategy. A web application firewall, or WAF, is a tool that can assist in mitigating a layer 7 attack. By putting a WAF in between the internet and an origin server, the WAF may act as a reverse proxy, protecting the targeted server from certain kinds of malicious traffic. By filtering requests based on a series of rules used to identify the DDoS attack, Layer 7 attacks can be impeded. One key value of an effective WAF is the ability to quickly implement custom rules in response to an attack. Anycast network diffusion is a mitigation approach to scatter attack traffic across a network of distributed servers to the point where the traffic is absorbed by the network. It's like channeling a rushing river down separate, smaller channels. This approach spreads the impact of a distributed attack to the point where it becomes manageable, and it diffuses the disruption. The reliability of an Anycast network to mitigate an attack is dependent on both the size of the attack and the size and the efficiency of the network. An important part of the DDoS mitigation implemented by Cloudflare is the use of an Anycast network. Cloudflare has a 10 terabit per second network, which is an order of magnitude above the largest DDoS attack ever seen. Now I'm going to do a deep dive into several kinds of DDoS attacks. A Udp Flood attack is a type of denial of service attack in which large numbers of user datagram protocol packets, or UDP packets, are sent to a targeted server with the aim of overwhelming that device's ability to process and respond. The firewall protecting the targeted server can also become exhausted as a result of UDP flooding, resulting in denial of service to legitimate traffic. A UDP flood works primarily by exploiting the steps that a server takes when it responds to a UDP packet. Under normal conditions, when a server receives a UDP packet at a particular port, it goes through 2 steps to process. First, the server checks to see if any programs are running which are presently listening for requests on the specified port. If no programs are listening at that port, the server responds with an ICMP ping packet to inform the sender that the destination was unreachable. It can be thought of like a hotel receptionist taking routing calls. First, the receptionist receives a phone call where the caller asks to be connected to a specific room. The receptionist then needs to look through a list of all the rooms to make sure that the guest is available and that they're willing to take the call. But once the receptionist realizes that the guest is not taking any calls, they have to pick the phone back up and tell the caller that the guest will not be taking the call. If suddenly all the phone lights light up simultaneously with similar requests, then the receptionist will be quickly overwhelmed. As each new UDP packet is received by the server, it goes through these steps. In an attack, during this type of DDoS attack, the attacker will not use their own real IP address. They will instead spoof the IP address of the UDP packets, which helps impede and hide the attacker's true location, and also prevents them from becoming potentially saturated by any ICMP ping responses. As a result of the targeted server utilizing resources to check and then respond to each received UDP packet, the target's resources can be quickly exhausted when a flood of UDP requests are made, resulting in a denial of service to normal traffic. Most operating systems mitigate UDP flood attacks by limiting the response rate of ICMP packets, in part to disrupt DDoS attacks that require ICMP response. One drawback of this kind of mitigation is that during the attack, legitimate requests may also be filtered. If the flood has a high enough volume to saturate the state table of the targeted server's firewall, any mitigation that occurs at the server level will be rendered useless, as the bottleneck will be occurring upstream from the targeted device. Cloudflare mitigates UDP flood attacks by dropping all UDP traffic that's not related to DNS at the network edge. Because of our Anycast networks, we have the ability to scatter web traffic across many data centers, so we have sufficient network capacity to handle UDP flood attacks of any size. The next kind of attack I'm going to describe is a Syn Flood attack. A Syn Flood is also known as a half-open attack, and it's a type of DDoS which aims to make a server unavailable to legitimate traffic by consuming all available server resources. By repeatedly sending initial connection requests or SYN packets, the attacker is able to overwhelm all ports on a targeted server machine, causing the targeted device to respond to legitimate traffic sluggishly or not at all. Syn Flood attacks work by exploiting the handshake process of a TCP connection. Under normal conditions, TCP connections exhibit 3 distinct processes in order to make a connection. First, the client sends a SYN packet to the server in order to initiate the connection. The server then responds to that initial packet with a Syn ACK packet in order to acknowledge the communication. Finally, the client returns an ACK packet to acknowledge the receipt of the packet from the server. After completing the sequence of packet sending and receiving, the TCP connection is open and able to send and receive data. To create denial of service, an attacker exploits the fact that after an initial SYN packet has been received, the server will respond back with 1 or more SYN ACK packets and wait for the final step in the handshake. Here's how it works. The attacker sends a high volume of SYN packets to the targeted server, often with spoofed IP addresses. The server then responds to each one of the connection requests and leaves an open port ready to receive the response. While the server waits for the final ACK packet, which never arrives, the attacker continues to send more SYN packets. The arrival of each new SYN packet causes the server to temporarily maintain a new open port connection for a certain length of time, and once all the available ports have been utilized, the server is unable to function normally. In networking, when a server is leaving a connection open, but the machine on the other side of the connection is not, the connection is considered half open. That's why this attack is often called a half-open attack. The targeted server is continuously leaving open connections and waiting for each connection to time out before the ports become available again. A Syn flood can occur in 3 different ways. A direct attack is when the IP address is not spoofed. The attacker does not mask their IP address at all. In this kind of attack, since the attacker is using a single source device with a real IP address, the attacker is highly vulnerable to discovery and mitigation. A malicious user can also spoof the IP address on each SYN packet they send in order to inhibit mitigation efforts and make their identity more difficult to discover. While the packets may be spoofed, these packets can potentially be traced back to their source. A distributed attack is created using a botnet, and the likelihood of tracking the attack back to the original source is very low. For an added level of obfuscation, attacker may have each distributed device also spoof its IP address. If the attacker is using a botnet, such as the Mirai botnet, they generally won't care about masking the IP address of the infected device. By using a Syn Flood attack, a bad actor can attempt to create a denial of service in a target device with substantially less traffic than other kinds of DDoS attacks. Instead of volumetric attacks, which aim to saturate the network infrastructure, Syn attacks only need to be larger than the available backlog in the target's operating system. If the attacker is able to determine the size of the backlog and how long the connections remain open before timing out, the attacker can target the exact parameters needed to disable the system, thereby reducing the total traffic to the minimum necessary to create denial of service. A Syn Flood attack can be mitigated. This vulnerability has been known for a long time, and there are a number of ways to mitigate. Here are some approaches. You can increase the backlog queue. Each operating system has a certain number of half-open connections that it will allow. One response to high volumes of Syn packets is to increase the maximum number of possible half-open connections. In order to successfully increase this maximum backlog, the system must reserve additional memory to deal with all the new requests. But if the system does not have enough memory to be able to handle the increased backlog queue size, then system performance will be negatively impacted. Another mitigation strategy is recycling the oldest half-open TCP connection. This strategy requires that the legitimate connections can be fully established in less time than the backlog can be filled with malicious Syn packets. However, this particular defense fails when the attack volume is increased, or if the backlog size is too small. Finally, you can utilize Syn cookies. This strategy involves the creation of a cookie by the server. In order to avoid the risk of dropping connections when the backlog has been filled, the server responds to each connection request with a Syn ACK packet, but then drops the Syn request from the backlog, removing the request from memory and leaving the port open and ready to make a new connection. If the connection is a legitimate request, and a final ACK packet is sent from the client machine back to the server will then reconstruct, with some limitations, the Syn backlog queue entry. While this mitigation does lose some information about the TCP connection, it is better than allowing a denial of service. Cloudflare mitigates Syn attacks, in part by standing in between a targeted server and the Syn flood. When the initial Syn request is made, Cloudflare handles the handshake process in the cloud, withholding a connection to the targeted server until the TCP handshake is complete. This strategy takes the resource cost of maintaining connections with bogus Syn packets off of the targeted server and pushes it into Cloudflare's Anycast network. What is a DNS flood? Domain name system servers are the phone books of the internet. They are the path through which the internet devices are able to look up specific web servers to access internet content. A DNS flood is a type of denial of service where an attacker floods a particular DNS server in an attempt to disrupt DNS resolution for that domain. If a user is unable to find a phone book, it cannot look up the address in order to make the call for a particular resource. By disrupting DNS resolution, a DNS flood attack will compromise a website, API, or a web application's ability to respond to legitimate traffic. DNS floods can be difficult to distinguish from normal heavy traffic because the large volume of traffic often comes from a multitude of unique connections, querying for real records on the domain, mimicking legitimate traffic. Let's look at how a DNS flood attack works. The function of the DNS system is to translate between easy-to-remember names like example.com and hard-to-remember addresses of website servers like 192.168.0.1. So, successfully attacking DNS infrastructure makes the internet unusable for most people. DNS flood attacks constitute a relatively new type of DNS-based attack that has proliferated with the rise of high-bandwidth Internet of Things botnets like Mirai. DNS flood attacks use the high-bandwidth connections of IP cameras, DVR boxes, and other IoT devices to directly overwhelm DNS servers of major providers. The volume of requests from IoT devices overwhelms the DNS provider's ability to provide answers and prevents legitimate users from accessing the DNS servers. How can these be mitigated? These DNS floods represent a change from traditional amplification attacks. Because of the easily accessible high bandwidth botnets, attackers can now target large organizations. Unfortunately, until compromised IoT devices can be updated or replaced, the only way to withstand these types of attacks is to use a very large and highly distributed DNS system that can monitor, absorb, and block the attack traffic in real time. Cloudflare's DDoS protection is an example of such a network. Cloudflare sees 10 million requests per second, services 10% of the internet requests every day, possesses over 100 data centers globally, services 2.5 billion monthly unique visitors, and covers 6 million websites, apps, and APIs in 150 countries. I'm Suzanne Aldrich. I've been your speaker today. My contact information is on this slide, and I'm very happy to take questions. Yes. It's been anticipated that the proliferation of IoT devices would eventually lead to these kinds of attacks. As you know, many of these devices are connected to the network and are not necessarily secure. Many of these devices are shipped with default passwords, which makes it very, very easy for an attacker to gain control and add them to their botnet. We believe that the 1 terabit per second attack that was performed on one of our customers last year was potentially caused by an IoT network of security cameras. We haven't confirmed exactly if it was the Mirai botnet, but we anticipate that in the future, these attacks are just going to become more and more common, partly due to the fact that manufacturers have very little to no incentive to update these devices. One interesting development that started yesterday is Senator Mark Warner of the United States has introduced some legislation which would require any devices shipped to the United States to have better security. We hope that this legislation is successful. We want to see Internet of Things be successful, but given that these devices are so hackable now, it's a little scary, and we hope that users who are looking for protection are able to find some shelter under services like ours. We have started working on a project we call Orbit at Cloudflare, which involves placing Internet of Things devices behind our proxy. This would allow these Internet of Things devices to be having a WAF in front of them. That way, if there is a vulnerability in the device specifically and the manufacturer is using our service, they can patch their software in the cloud before the owners of the device can update the software on the device. Another way that we think that we can help mitigate Internet of Thing attacks is with mutual client authentication. This would allow certificates to be installed on each of these devices. That way, the manufacturer can validate that it truly is the device that is connecting and not a rogue device. Does that answer your question?
他にご質問あったらご報告